Alright, hello everyone, I am glad to greet you all here today, and today we continue our journey into the reinforced learning world. In this lecture, we start speaking about model-free approach, when by model, we assume the model of the environment. So we shall discuss how can we actually interact with the environment if we don't know anything about its inner dynamics. We don't know probabilities of states, probabilities of transitions, and so on. And actually, it's the main case when we face some real-life problems. So, today we start with model-free learning, and here is the outline of today's lecture. First of all, we shall discuss the previous lecture material. Remember what is value function, what is Q function, how are they related to each other, and what are actually Bellman equations. After that, we define this dichotomy between model-free and model-based learning, where the model, once again, is the model of the environment, and discuss Q-learning as one of the mostly popular approaches to model-free learning. Actually, even people who never did something in reinforced learning usually have already heard about Q-learning because this technique is rather popular. After that, we discuss several approaches to estimate Q function, for example, Monte Carlo approach, temporal difference, understand why it is actually possible, and introduce several more algorithms which are kind of similar to learning, like SERSA, expected value SERSA, and so on. By the end of this lecture, also, you will know what is the difference between on-policy and off-policy learning, at least slightly see this difference. And we also discuss the engineering approach, which speeds up convergence a lot in some cases, which is named experience play. So here we start. First of all, let's remember, what is VP of S? Actually, VP of S is value function from the state S under the current policy P. So it's the expected cumulative reward from state S and so on till the end of the session if we follow exactly policy P. And we assume that there exists some kind of optimal value function, so it shows us the expected reward if we follow the optimal policy P with a star. Same stuff can be said about Q function. So Q function is almost the same as value function, but it shows us the expected cumulative reward from state S if we first take the action, we have here action A, and after that, after the transition we got because of the action A, we follow policy P till the end of the session. So actually we get reward for action A at state S, and then we just follow policy P, so we just take our discounted by gamma factor value function from next state. So same stuff with Q star, so it's some kind of optimal Q function where our policy assumed to be optimal. So actually, optimal Q function should be greater or equal than any Q function in our environment, and so on. And we have these two beautiful equations, especially Bellman equality, optimality equations, for Q star and V star. We can say that actually Q star is the expected value of the reward for action A in state S, plus gamma multiplied by V star, and V star is just maximum out of all possible Q functions for all possible actions in state S. And as you can see, we can constitute V star in here and see that actually it's reward plus gamma multiplied by a maximum Q function and so on. And here is just an example. We have some kind of trajectory within our environment. So we started in some state, then we selected action A, transition to next state, and so on. And at every step, we either get some kind of reward if we get it for every step, or we get it only in the end of the environment, in the end of the session, or every n steps, and so on. It depends. So we have two different situations, model-based and model-free approaches. In a model-based approach, we actually assume that we know probability of transition, which depends on stated action, and this allows us to apply some dynamic programming, use some kind of value iteration, policy iteration we discussed on the previous lecture, and we just can plan ahead because we actually know all the rules the environment is using to behave. Of course, when we speak about some kind of slot machine or self-driving vehicle or some ad program on the internet, anything, we usually don't know this exact dynamics, we don't know this distribution. That's why we cannot plan ahead assuming that we know it. That's why we're working in model-free approach, so we can only sample trajectories. So we just sample our action from our policy because policy is the thing we possess. Try some stuff out, and we don't have any guarantee, any insurance that our agent won't make some bad choices. So here is a question. If we have a sequence of states, actions, and rewards, and we can only sample trajectories, what should we actually learn? The value function or the Q function? So once again, we have no idea about the probability of next state conditioned on the current state and action because it's the model of the environment, we don't possess it. We only possess states, action, and rewards in the current trajectory we had played right now. So trajectory is just sequence of our solutions and recording of the responses of the environment. So what do we learn to actually find optimal policy? V function or Q function? Okay, 3, 2, 1. I guess it's kind of obvious that we need Q function, unless I hope now it's obvious when you see it on the screen. You can pause the video if you have some questions in here and try to think it over. So if we have only value function, so we know only the quality of every state, ignoring the possible actions, then we don't know which action to choose. We know just, all right, this position is rather good, so what do I do now? No idea. Actually, when we have Q function, we have a bit more information because now we know exactly which action is how good in every possible state. And we can just select the best action right now, then transit to the next state and repeat. So value function is kind of useless without probability of transition, while Q function is kind of useful. So we'll use Q function next to try to learn something without the model of the environment. And let's actually go there. So imagine we have some kind of policy. So it samples somehow our next action from some kind of distribution. And we want to find the Q function. How could we actually do it? For example, let's say we started from original state, played several games, and then we just take all the information from these several games and choose all these trajectories as our training examples. So we can actually estimate our cumulative reward for each trajectory, average them to get expectation, and then we can somehow estimate our Q function, right? So what is Q function? Expected reward for the next transition, just like we said it, plus gamma multiplied by value function of the next state, which on its turn is actually maximum out of all Q functions over all actions. So if we have a lot of trajectories, we just use Monte Carlo to sample them, then we can estimate it somehow. Of course, because we only sample several trajectories, not infinite number of them, we won't have the exact mathematical expectation. Instead of that, we only have some estimation of it, but still we can try to approximate it. But actually, using Monte Carlo might be really time consuming, because imagine you used just, I don't know, 10,000 of trajectories to get some good estimation. So you played 10,000 games with an agent which doesn't know anything, because agent is based on the policy, which is now useless. So we just used a lot of computational resources for no reason. And if you imagine some kind of real life simulators, for example, we were using real robot, which was trying to learn how to walk. And with bad policy, we have high probability just to break this robot. Kind of not so good. So there is another really beautiful idea. What if we use temporal difference and try to improve our Q function iteratively on every step within our environment? So here it is. Let's say on the right side, we have expectation of our reward for this transition plus gamma multiplied by actually value function of the next state. But now let's say we only have this idea that this is optimal Q function. Okay, this estimation of Q function is closer to the optimality because we've got new information from the environment. This is reward. So then we can just assign our Q function in state T and action A exactly this value, because actually at the beginning we just had some Q function in here, then we got new reward and proceeded to the new state, so we got some information on the environment. And it's aligned with Bellman equations, because if you take a look in here and remember Bellman equations, you can see that for the optimal policy, the optimal Q function will be exactly equal to the equation, to the formula on the right. So Q function can be improved iteratively, step by step, except we don't know how to compute the expected value, right? Because we don't have the probability distribution for the reward. So what do? Like always, if we can't get something explicitly, let's just estimate it. For example, expected value, use just sample average, for example, sample different, once again, trajectories and get it. So, for example, expected reward plus gamma by maximum Q value is some kind of average reward plus gamma, once again, by maximum Q value. And actually, to make our estimation even better, make it more optimal, we can use the exponential smoothing. So we actually take our old Q value right now, here and now, and include the update with weight of alpha. Alpha is just number between 0 and 1, so here is classical exponential smoothing. So once again, what's going on when we are speaking about temporal difference? Let's say we already have some kind of Q function, right? Then even if we just played not one game even, if we made just one step within our iteration environment, so after one iteration, we already get some reward. So we just have a sample of size 1, so the mathematical expression of the reward will be the reward itself. And we, of course, have our Q function for the next state where we got into. So we already can update our Q function even after one step, instead of sampling several trajectories as we did before. So even during one session, we can learn a lot about our environment. And that's actually the main idea about temporal difference. We use that fact that we can move in our environment step by step, and that fact that we actually accumulate some information from the environment with every reward we actually get. Here it is. And here is beautiful visualization. I hope it will be a bit easier. So let's say we've been in state S, we transitioned to state S prime, we already did action A, so we already know where did we get, and we got reward error. After that, we have several possibilities to make action 0, 1, 2, 3, till E. And what do we do actually? First of all, it's applicable to any kind of position except 0. At 0 position, we just made some choice, transition to first position, and now we can just use our Q-learning. So let's say at the beginning, when we have never seen this environment before, we can initialize our Q function with zeros. Okay, so all zeros for all actions and all positions. To make it even simpler, let's for now assume that we're speaking about tabular case, so we have fixed number of actions, fixed number of states. So we're just speaking about some table where for every action and state pair, we have some value. After that, we sample state, action, reward, state, prime from the environment. So we just select some kind of action. So we have this cortege of information, this tuple. And after that, we can compute our new Q function estimation. So our new Q function estimation will be actually a reward we got for this transition, plus gamma multiplied by maximum Q value of the next state. And when we have our new Q value, Q function estimation, we can just update our Q function by exponential smoothing. Actually, we use exponential smoothing for several reasons. For the easiest explanation might be that if we got some really bad example in here, then we still don't forget what we had before. We only add it with alpha coefficient. Usually alpha is not that big. So about maybe 15%, 25%, and so on. And we repeat it again and again. And after every transition, we already get some more information on the environment, and our Q function is now not filled with zeros. Even after the first transition, we already know something about this particular transition from state S with action A. And that's kind of useful. So, once again, here is Q-learning. We assume that for optimal policy, for optimal Q function, we have this equation hold. So we try to use this update rule to find our optimal Q function. Actually, it should converge to our optimal Q function. And when we have our optimal Q function, then we can explain what we're going to do. We are going just to select the best action according to the Q function on every step, step by step by step. Right. Only seems like we've got a problem here. So we'll get to this problem. Right now, let's just summarize what we discussed. So our goal right now was to estimate the Q function. There are two approaches, at least the ones we discussed, to average Q over sampled paths, or just use recurrent formula for our Q function. Second approach is actually more quick, I would say. It requires less sessions to train something. First approach is more stable in some case, but it requires much more samples. So, Monte Carlo averages Q over sample space. It needs full trajectory to learn, but it's less reliant on Markov property because when we define this recursive formula, we assume that we have Markov property in our environment and next state and action only depends on previous state and action we selected. That's why actually we have this recurrent formula. Here it is. You see, we are only based in state t plus 1 on state t and action t. We ignore everything which was before, so we have some kind of Markov property. While temporal difference use recurrent formula for Q, it learns even from partial trajectories. It can work with infinite MDP. So imagine we have still Markov decision process, but it has no end. So we can just play this game till the end of the time. So we cannot sample several trajectories because they have infinite lengths. But temporal difference still will work. And it requires less experience to learn. Once again, here is Q learning. And now let's take a look at the policy and think, what actually is the problem? The problem is, if agent is greedy and always selects the best according to the Q-value actions, like we see here, our policy is actually argmax, so it is greedy. So we select best action, which delivers the highest Q-value. Then actually our agent is unable to find better actions, which it hasn't learned yet. So if our agent doesn't know anything about the environment, it selected first action, which actually shown to increase the reward. After that, it will always select this particular action in this state because it delivers the maximum Q value. All others have still zero. So kind of problem. That's why we need actually to fix it. Here is another beautiful example. Imagine we have a robot which is trying to learn how to walk. Initial Q value, once again, will be zero for all states and all actions. For example, actions are to change the angle in different joints, to change the voltage on the engines, and so on. And imagine robot uses greedy policy, as we discussed. So it did something, for example, fell straight forward or learned how to crawl. So it already got some positive reward for its movement. For example, reward was the distance it covered in some kind of fixed time. And then our robot knows that crawling is kind of delivering reward higher than zero. So Q function is actually not zero. It's the best Q function over all possible actions. And now our robot is just crawling all the time and it has no chance to learn how to walk because it selects greedily the best action according to our Q value. So we kind of need to fix it somehow. And this problem is a bit more general than simply problem of Q learning. That's why it's named exploration exploitation, problem exploration exploitation trade-off. So here we go. Actually, we need somehow to give our model, our agent, an opportunity to either explore something new in the environment. So to learn something new, like you don't walk outside in winter without a hat, something like that. Or you might catch a cold. And exploit its possessed knowledge at the same time. Actually, it's kind of really close to what we observe in our own lives, for example, in the education. After bachelor's, many of us had a choice, I guess, to continue educating ourselves, to continue studying, or just to go get a job somewhere and then get better reward if we're speaking higher reward if we're speaking about just money income. Because we can work even without higher education and still get some money, but usually higher education, if you really make a big effort, gives us more opportunities afterwards. So here is exploration exploitation in real lives. But speaking about agents and simple environments, it's kind of much more simple, at least right now, because we're speaking about just tabular cases where not so many actions, not so many states, and so on. So let's just define two possible approaches to fix the greedy behavior of our agent. First, actually, is really straightforward. So let's name it epsilon greedy policy, and let's say that we just select random action with epsilon probability. Epsilon is low number between 0 and 1 once again. Otherwise, we select best action according to the current Q function. So we just select random action with epsilon probability, and we select best action with 1 minus epsilon probability, so we act greedily. Actually, it will allow us to explore depending on the rate of epsilon with high or lower probability, but it has some probable problems as well. For example, our agent can just, I don't know, if we're speaking about robot which is trying to learn how to walk, it might get with epsilon probability action jump into the wall, break itself, kinda not so good. So there is another approach which is also widely used. It's named softmax approach. You all are familiar with softmax, I hope. So we just sample action from a distribution which we got from our q-values normalized by softmax function. So we have our q-values for all the actions in this particular state. These are just some logits with quotes, of course. Then we normalize it with softmax. Now we have probability distribution, discrete distribution for fixed number of actions. And then we just sample from this distribution, so we find our next action by sampling it from this distribution. Just in case, the tau parameter is the temperature of softmax. I guess you're familiar with it as well. So it defines how random our policy will be. If we have high temperature, then actually everything is kind of close to each other, so our distribution is closer to uniform. On the limit, if we increase temperature to the infinite, positive infinite, we just get uniform distribution. On the left limit, if we decrease temperature to almost zero, then we get just ergmax, and we select just the best action, so once again, it's greedy behavior. And here is actually a question to you, let's think it over. So we have two different approaches to exploration-exploitation trade-off. What do you think? When our agent doesn't know anything, is it a good idea to make epsilon high, low, or it doesn't matter? And speaking about the end of the episode, so after our agent, not actually end of the episode, end of the training process, so when our agent has already learned something, should epsilon be high or low compared to the beginning? Should it be higher or lower? Just let's think about it for several moments and then continue. So, beginning of the game, beginning of the training process. High epsilon or low epsilon? Actually, at the beginning, if we behave according to our Q function, which is dummy, it's useless, it doesn't know anything, it doesn't matter actually how high is epsilon, because our Q function is still useless, so we are already acting randomly. And if we just select some random actions, it won't actually break anything, we just explore our environment. But in the end, when actually our agent has already learned something, if we still act with high probability of random action, we just don't make good actions with high probability, and it's kind of not giving us a chance to have long sequences of some suboptimal actions. So usually epsilon is high at the beginning, and it decreases slightly till the end of the session. Maybe it might be stepwise function, it might be just linear decay, it might be some exponential decay, or any other decays. You can actually take a look at it and see that it behaves kind of similar to the learning rate in deep learning. When I was speaking about some convergence process, usually we prefer not to have fixed learning rate, but it decreases through the time, depending on our quality of the model, depending on the loss function surface, or something like that. Same stuff with softmax. So at the beginning, we appreciate more exploration because we don't know anything. So temperature might be higher. By the end of the session, temperature might become lower. But actually, if we prefer to learn something new, we still require some randomness in the behavior of the agent. Otherwise, it won't be able to learn anything new. So epsilon and temperature should not converge to zero if we are speaking about still exploring our environment. But for exploitation, for example, we trained our model, now we just need to get the best reward we can get in this particular game. Then we can just turn off the epsilon because we don't want random actions, we want best actions according to our current key function. Or we can just replace softmax with ergomax and select best actions as well. Actually, in this case, these two approaches will be kind of the same because we remove all the stochasticity from our policy. Now it's just defined by key function without any randomness. Okay, here it is. And let's take a look on the cliff world. Let's say we're speaking about the epsilon greedy policy. And we have gamma, discount factor gamma, just in case. Here it is. Here is our discount factor. of 0.99. We already discussed Q-learning, we discussed how to explore, not to be greedy, but still. Here is a really simple example. It's named Cliff World. So here is start position of our route. Here is our goal, I would say. So this is the only location where our agent gets reward equal to 10, and actually it wins the game, so the session is over. And imagine in here we have some kind of, I don't know, flames, bad place. So if agent gets here, then it gets reward -10, and the session is over as well. So which trajectory will Q-learning agent prefer if we use epsilon greedy policy and we have gamma discount factor of 0.99? Green one or red one? Just think about it for a while. So 3, 2, 1. I guess, okay, I don't know which one you selected, but actually the agent unexpectedly will prefer the red trajectory, while it has really high chance to break itself because of falling into the flames. Because actually we have here the gamma discount factor, so if you just take a look in here, when it goes along this direction, along this path, then in here we get reward 10, so in here we actually get 0 reward, plus gamma multiplied by the reward in the next state. So it's 10 multiplied by 0.99, 9.9. In here, we once again multiply by 0.99. So it's gamma squared, gamma cubed, 4th, 5th, 6th, 7th, 8th, 9th power. So actually, we multiply by gamma 9 times in here. Yes, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. And if we go along the red path, we multiply only 1, 2, 3, 4, 5, and 6. No, actually 5. 1, 2, 3, 4, 5. Yeah. So the trajectory which the agent prefers is the red one, despite it won't maximize the reward, because actually, according to our epsilon greedy policy, in some games it will just randomly pick action not to go to the right, but to go to the bottom, break itself, get negative reward, and so on. The problem is, in Q-learning, we select maximum Q value over all possible actions. So if in this location we have 3 possible actions, go up, go right, or go down, actually it doesn't matter whether we'll go down or go to the right, if we already learned something about the environment, so we at least once got along this path, then we already know that in here the Q value is the highest. So we just consider our best action, and our Q function shows us that going to the right is the best, because it gives us the highest cumulative reward, because cumulative reward is our reward at the end, discounted only by 5 multiplications by gamma, not by 9. So here is the Q-learning, and it got some problems. Any ideas how to fix it, actually? So the problem, once again, the problem is hidden in this maximum operation, because when we get maximum over all possible actions, we ignore how bad the situation might be. We only look how good might it be. So, like, if the agent is trying to play lottery, for example, if it won one time in the lottery, then it knows that, right, I can get lottery ticket, get huge reward, with relatively small chance, but still I can get it. So I wait. Okay, agent waits, while it will win. It has low probability of winning, but still it knows that it might be really great. So buying a lottery ticket is actually good according to the Q function action. So we need to fix it somehow. So we need to get rid somehow of the greedy behavior of our agent, and greedy behavior of Q-learning is actually hidden in this max operation, because we always select the best Q value over all possible, instead of selecting some kind of expected one or random one. So to fix it, let's try, for example, to use just random action sampled from our policy. Here it is. And it delivers us another algorithm named SERSA, and I guess it might be really obvious why it's named SERSA if you just take a look at the slide. So, instead of selecting best action from all possible actions, according to the Q value, we just sample random action. Okay, not random, sample action according to our policy from state S prime, get some reward, and that's it. And it's named SERSA because, actually, just read. We sample state, action, get reward, get to the next state, and sample the next section, and did Sarsa. So our update rule, our estimation, is now actually not taking into account maximum. Instead of that, we just sample action from our policy and get it. And getting back to the cliff world, actually, if you take a look at Sarsa, then you will see that Q function in here will be much lower this time because according to our policy, which is still epsilon greedy, now agent has 15% probability to, okay, 15% probability by 1/2, for example, okay, 1/1/3, to jump into the flames and get negative reward. And then here, it actually has no probability to jump in flames, so the reward will be higher, much higher. So Sarsa is giving us an opportunity to get rid of some kind of greedy behavior, but it also has some problems. For example, let's say we still have some strange, I don't know, policy. It's not well fitted, so actually our Q function is stupid right now, and we don't select the best action out of all actions. We just select random actions, and imagine we're only at the beginning of the training where we only know several not so bad actions and a huge variety of bad actions, but we still randomly pick one of them, and that's it. We can try to fix it a bit by introducing not just simple sampling procedure, but by introducing the mathematical expectation. So once again, we get to the next state. Now we take our policy, and now we compute the expected value of our Q function for every action in this potential state where we are located. And now, instead of simple sampling of the next action, we actually think, what will happen if we select action 0? Let's compute the expected value of our Q function according to our policy. So Q function of action 0 will be weighted with probability of action 0. Q function of action 1 will be weighted with probability of action 1 from our policy, and so on. And after that, we use the same update. So EV-Sarsa also has really good properties, but actually they are different. Q-learning Sarsa and EV-Sarsa are different, so we cannot say that EV-Sarsa is always the best. We cannot say that Q-learning is always the best. They are well suited for different situations. And here we come to really big difference in the reinforced learning approaches. We have on-policy and off-policy methods. So what's actually going on with on-policy? When we speak about on-policy, so I don't know, imagine a horse and agent is sitting on the horse, so it's sitting on its own policy. So it trains on the experience only it generates with its own policy. So agent played, I don't know, game of chess, then it trains on its own experience. And the idea is, we assume that all the samples we're training on are generated from the same policy we're actually trying to update. So here it is, you see? Here we use our policy, right? We just sample an action and we use it. When we're speaking about off-policy, we are speaking about some external information, samples, state accretion, reward states, sequences, which weren't generated under the current policy. Instead of that, we assume that they were generated by any other policies. And for example, we can try to train on some external data in the off-policy manner. Imagine we're trying to learn how to play chess, for example. We can either learn how to play chess from scratch, so our agent just tries to play with itself, for example, self-play for a long time, or just, first of all, take just a lot of different Grossmeister games and show our agent that these movements were actually good because they led to the winning, and these weren't actually good because after them, the Grossmeister lost, for example. And you can see here that we already have examples. It's not a question right now, just to define them. So Q-learning is actually selecting best action according to the Q function. The Q function actually shows us it's not the policy itself, it's just Q function from which we actually get the policy. That's why it's off-policy method, because this Q function can be trained on the policy of the agent itself. It can be trained on some external examples. For example, as we said, we just selected a bunch of games from Grossmeisters, then learned our Q function from these games, and then try to upgrade it by make it better by training further with Q-learning. EV-Sarsa is also off policy because in here, while we estimate our Q function estimate our future Q function from our policy, we still might get this Q function from actually anywhere. But when I'm speaking about Sarsa, we sample our action from our policy. That's why we're still sitting on the horse. This might be a little bit confusing right now. I understand, at least for me, when I seen the off policy and on policy difference, it was really strange. So I would say that the main idea in here is from where are the actions coming? Are they coming from our current policy, under which we actually evaluate our Q function and its updates? Or they are coming from external data, which can be any, actually. So the difference is here. When we're speaking about Sarasa, we only can train on our own experience. That's why it's definitely on policy. Cross-entropy method, for example, is also on policy, at least in the statement we discussed on the first lecture. So just take our policy, sample trajectories from this policy, select best of them, train on them, and repeat. While when we're speaking about Q-learning, we can actually train on any samples. They're not samples from our current policy. In here, we just select all possible actions, compute Q value, and select maximum Q value. So here it is. And I hope this dichotomy is a bit straightforward, more straightforward than it was before. If you have still feeling that it's kind of not so understandable, please ask questions. We'll cover it once again on the upcoming lectures, and then once again, because we'll discuss different methods, define when we can treat them as on policy, off policy. I just want to clarify that all off policy methods, of course, can still train on policy as well. For example, in Q-learning, in here we might get actions only according to our policy, then no problem. But we also can get this Q function from somewhere else. But in Sarasa, we cannot get actions from external because we just don't have such chance. We just need the action from our current policy. We get Q function, we update it itself, and so on. All right, here we go. And finally, one additional technical stuff I would say we need to discuss, because I guess you understand that training our model might be really complex, especially if we imagine some complex games like, I don't know, there is a beautiful game Halite from 2 Sigma, which is a good environment for reinforced learning. Maybe we'll cover it on one of the classes, but I guess it's a bit too complex just for setup to run in class. Maybe we'll have some optional lab assignment on it. So, what I was saying, interacting with some complex environment, just imagine, I don't know, playing the game of Doom, just the old one from the 90s, where you still need to render all the 3D space, then all the states will be image of the input, what you see on the screen, and every action is actually go left, right, shoot, and so on. So to get a new example, our agent actually needs to render all the area within the game, make some step, then record it, make update, make new step, and so on. And when we are trying to get a lot of examples to train on, for example, I don't know, 10 in power of 4, 10 in power of 5 examples to get really good estimation of our Q value, then it might be really time consuming because we need to run several games simultaneously on the same machine, and it might be just not enough computational resources to generate new data at every step. So people just decided, why not to use previous just tuples of state action reward state, which were generated by our agent before, and then just use them once again to update our Q function. So here is the idea. Let's say we have our agent, it interacts with the environment, so we get state action reward state tuple, and after that we just add it to some replay buffer. And we store only, for example, the last 1,000 or 10,000 or last million of interactions. After that, instead of selecting the new current input, we just randomly select batch out of this replay buffer, train on it, and repeat. One could say that, wait, it will actually make things worse because we are getting some kind of bad examples from previous times where our policy was weaker and still train on them. And yeah, you would be right. But actually, experience replay has one additional property. It has it is a fix to one additional problem, which is actually a topic of the upcoming lecture, but I still want to cover it briefly right now. When I was speaking about our agent, which is training on policy, it's training on its own experience. And imagine we're speaking about some game, I don't know, once again, some game where the agent needs to shoot. For example, Space Invaders of Atari. So just there are aliens on the top of the screen, some spacecraft on the bottom of the screen. Spacecraft might shoot, and it might just hide under the rock, so it's not being shot. And imagine for some reason our agent got under the rock and stayed there for some time. So it already forgot how to shoot, and when it just getting from beneath the rock, it gets shot, it gets negative reward, and it learns that getting from under the rock is kind of a bad idea because the reward is negative. So it just learned to stay under the rock, forgot how to shoot, now it's unable to get away from it. Actually, that's a problem of on-policy algorithms because agent trains on the experience it generated by itself, so our training samples are actually conditioned on the policy. And policy is actually conditioned on the training samples once again. So we have some positive loop in here, loop of interactions. So when we are trying to use experience replay, we're actually getting more ID information, we're getting more ID samples, because if we remember something from long past, not in our policy already, but in our replay buffer, we still remember how to shoot, how to play. That shooting might be useful as well, because these are examples from different locations in our environment. So we're not sitting inside this, I don't know, under this rock for the whole time. We're trying many different examples to make things a bit better. So, once again, idea: store several past interactions, state, action, reward, state, train on random subsamples, and we just play one step, record it, then pick random transitions to train, and repeat. Actually, profit, we don't need to revisit same state action many times to learn that actually action A is good in state S. And if you realize that our update rule is actually exponentially smooth, otherwise we need to visit this location several times with this action to remember actually that it is really a good action. So, kind of that. And just a question to you: can it be applied to off-policy learning or to on-policy learning or both? So, the question: can it be applied off-policy? Of course, because when I was speaking about off-policy learning, we can train on any kind of experience. For example, our past experience. Can it be used in the on-policy approach? Actually, no, because these tuples, state, action, reward, state, were generated under the previous wiki policy, and actually, that's definitely not on-policy situation. All right. I hope right now you get a brief just feeling what's going on. Q-learning is still, I guess, not so clear how does it work, because it's just a new technique and it's really not so simple. So I just want to ensure that you got the main idea. So we have the Bellman equations from the previous class and from just Bellman, and we assume that our best policy is aligned with some best Q function, which is actually equivalent. It has the equality, so best Q function is equal in every state and every action with expected reward for the state action transition plus gamma multiplied by the value of the next state. And to get there, we actually use this update rule. So we use our Q function, current Q function, and we try to update it by interacting with the environment and getting some new reward and learning where did we get. And just to clarify, here is exactly the link of the information in Q-learning. Before we interacted with the environment, we just knew our Q function. But after we interacted, we got the reward. Actually, this is our signal. And in addition, we got information where did we get, in which state. So this is exactly what we are trying to accumulate in our Q function. We accumulate what was the reward, and we accumulate where will we get. And that actually clarifies why we can use Q-learning for model-free learning. Here it is. Here it is. Because when we are trying to learn something about the environment within our Q function, we're actually implicitly building the model of our environment. Now our Q function actually not builds the model of the environment in general, but instead of that, it just remembers which actions in which states are delivering higher probability of getting high reward just by this simple update rule. And just in case, it's really good idea in some cases not to learn the model of the environment, because in some cases learning the model of the environment might be much more complex than just learning how to exploit it. For example, to brew some coffee, you don't need to know how does the coffee machine work under the hood. You don't need to know what are the chemical processes going on when you brew some coffee. Instead of that, you just push a button, put in some coffee, push a cup, and here you are, up and ready to listen to another lecture. Okay, so here is the main idea. Q-learning is implicitly learning the structure of our environment. It's not defining the probability of all transition and all the states. Instead of that, it's learning the reward function, I would say, which is conditioned on probability of transitions and states. And here we are. So, actually, on the practice session, we shall cover Q-learning in depth on, once again, simple environment for the first time. So we'll just use tabular situation. And since next week, we actually start speaking about some deeper stuff. So we shall speak about deep learning, how to apply neural networks to all the situations, and how to actually fix it. So here is a brief outro for this lecture. Q-learning allows to learn some approximation of the reward function, and actually it's a proxy to our environment model. And just so you remember it, maybe, this idea with proxy is really easy to understand. So we don't know the model of the environment, we don't know how to interact with it. So instead of interacting with the environment, we first learn some kind of proxy function, our Q function, which shows us which behavior is bad or good. And after that, using this Q function, we define our policy. Just as we discussed, we can define it with many different ways, for example, as softmax from our Q function. So Q function is some kind of proxy. And please remember what is the difference between Q function and V function, value function, because Q function has additional degree of freedom. It allows to select the action here and now, ignoring the policy, just the action we selected right now. Exploration exploitation trade-off is present everywhere, in real life, in reinforced learning, so just dare to explore, as I would say. But don't forget to exploit your possibilities as well. And remember the main difference between off-policy and on-policy we discussed in this lecture. We'll visit this difference again and again. But otherwise, please stay safe, ask your questions if you have any, and see you next time. Take care.